This is the third part of the first lecture of week 12, where we'll discuss another example of text problem where we may get the linear system of differential equations. And the example is in electrical systems. And electrical system, you can see an example of electrical system here, which may contain, first of all, some electrical source, and then capacitor, resistor, and inductor. So we will use, to solve such problems, we'll use first of all the Kirchhoff's law here, and also the knowledge that the current is in fact the derivative of charge with respect to t on the capacitor. And this problem here, this particular problem here, we're given that we're given this electrical circuit, and we need to find what is the currents, what are the currents in the various branches of this circuit. So for example, if we start from the electrical source, we have the current I1, which goes through the resistor here, and here it splits into two currents, I2 and I3, and after they come back at a point B, they combined into again one current I1. So we have to find these three currents, I1, I2 and I3, which of course the functions of t. And since we have three unknowns, we must get three differential equations. And we will split this circuit into three loops, and we will consider the loops separately. So we see the first loop is shown here, the second loop is this big one, and the third loop is this one. So let's discuss each loop separately. So what we have in loop 1, for example. Here we have the electrical source, which will be E of t here. We have the inductor, which will give us this term of the Kirchhoff's law, and we have resistance, which will give us the second term in the Kirchhoff's law. So let's substitute these things into this law here. So first of all, we get this inductor here. So it's 1 times di dt, and here the current is I2. So di2 over dt plus R is given, this is 20, and the current through this resistor is I1, so times I1. We don't have capacitor here, so this part is 0, and the electrical source gives us 5 volts, so 5 on the right. This is loop 1. Let's discuss what we have in loop 2. In loop 2, this is the big loop here. We have again the electrical source, we have the resistor, and also we have capacitor here. And so this part now is 0 because we don't have inductor here. And here we have 20 times I1 plus, and through the capacitor we have the current I3, and I3 will give us the charge Q3. So let's say 1 over C, and we're given 1 over 160 farad. So if we revert it, it will be 160 Q3. And this must be also 5. And in loop 3, this loop here, we have no electrical source, so the right hand side will be 0. We have the inductor, so this part will be not 0, and we have also capacitor. So here through the capacitor we have the same thing, 1 over 160 Q3, and we assume in fact everywhere that the direction like this is positive direction, so I2 goes to reverse directions, so we must use minus, and here we have 1 times the derivative, so di to dt times 1, so nothing, no coefficients, and this must be 0. We can notice here, if we take the equation for loop 2 and take the difference with the equation for loop 3, then we obtain exactly the equation for loop 1. In fact, it means that these 3 equations are linearly dependent. And since we have 3 unknowns here, I1, I2 and Q3, it means that this amount of equations is not enough to solve it. And therefore we need something else. And this something else that I forget to write is this step here. When the current I1 comes through the point A, it's split into 2 currents I2 and I3. So the additional equation is this one. And now we need to connect I3 and Q3. So the current is the derivative of the charge. So in fact here we have 4 equations and 4 unknown functions: I1, I2, I3 and Q3. Let's also now think about initial values. So it's given that at the time t, it's here in the problem, the charge on the capacitor, so Q3 at the time 0, this is 2, and the current through the capacitor, so this is I3 at the time 0, is 0. So in fact this is the same as Q3 prime of 0, so we'll use one of these initial values. Okay, let's try to solve this problem. So here I wrote the equations and the initial values. So let's think what can we do to get rid of some unknowns. The first thing, we can replace I3 with Q3 prime. So I1 is I2 plus Q3 prime. And next we can replace I1 here and here. What do we get? I2 prime plus 20 I1, so I2 plus 20 Q3 prime is 5. And the second equation, 20 I2 plus 20 Q3 prime plus 160 Q3 is 5. So now we have just 2 unknown functions. And here we can find I2, for example, from the second equation. So I2 is 1 over 20, 5 minus 20 Q3 prime minus Q3, and substitute it into equation here. So the first thing, we need to find I2 prime. So maybe we should rewrite it first. 1 over 4 minus Q3 prime minus 8 Q3, and then substitute it here. So I2 prime is now minus Q3 double prime minus 8 Q3 prime plus 20 I2, so multiply by 20 we get just this thing, 5 minus 20 Q3 prime minus this thing, Q3 plus 20 Q3 prime, this is 5. Okay, let's combine everything that we have here. These two can be cancelled, so overall we get, and 5 also can be cancelled. And let's multiply everything by minus 1, so we get Q3 plus 8 Q3 prime plus 160 Q3 is 0. So we get homogeneous linear equation with constant coefficients with respect to this Q3 function. Next, we need to find this Q3, and we also have the initial values for Q3, so this is good. We can find precise function for Q3. Let me just write the answer. So solve this. We find Q3. This is 2e to the minus 4t cosine 12t plus 2 over 3 e to the minus 4t sine 12t. Okay, so we have the value for Q3. Now, what we have to do, we can find, for example, I1 from the second equation, right? So find I1, which is 5 minus Q3 over 20, and I1 is 1 over 4 minus, you can just check this because I'm not going to do this. This is not so difficult. You can do this by yourself. Minus 16 over 3 e to the minus 4t sine 12t. So you know I1. You can know also I3, right? I3 is I3. This is Q3 prime. So just take the derivative. Okay, when we take the derivative overall, we get minus 80 over 3 e to the minus 4t sine 12t. And now to find I2, we take just I1 minus I3. And the answer for I2 is 1 over 4 minus 16 e to the minus 4t cosine 12t plus 64 over 3 e to the minus 4t sine 12t. So let me just indicate the answers. So we find Q3 from solving this differential equation with these initial values, which we of course can do. Then find I1 using Q3 from the second equation here. So I1 is this value. Then find I3, which is just the derivative of Q3. And then I2 from the third equation, which is I1 minus I3, and we get this thing here. So that's it. This is the end of the solution of this problem. So we solved this given system and these initial values here using just some algebraic manipulations. And you can ask why we didn't use the Laplace transform approach here. Because if you try to do this, you see, for example, for I2 here, if you use Laplace transform, you need the initial value of I2, which is not given in this problem. So in fact, the Laplace transform approach is not applicable here. So this is in fact an example of system where you can only use the algebraic approach. And let me now give a summary of Laplace transform. Of course, the first thing that you have to learn is definition of Laplace transform. So the first thing, of course, is definition of Laplace transform. You have to learn it by heart. No one will remind you the formula for this. And also you have to know how to apply all properties. For example, linearity, for example, that Laplace transform of, let's say, some combination will be A, F plus B, L, G. And in fact, all other properties except this linearity will be given to you in a table on the final exam. So all other properties will be given to you. And let me show you which table will be given to you on the final exam. So you open the book and you go to the final page of this book. So this is 719. So exactly this table will be given. So you see, the first column and the third column of this table are some functions, and the second and the fourth columns are Laplace transforms of these corresponding functions. And for example, here you can find Laplace transform of t to the n. So this is the function, this is its Laplace transform. This is a function here, e to the at, this is its Laplace transform, and so on. So the second column, if you, let's say, need Laplace transform of cosine, you find cosine, and the Laplace transform is here. And also you can find some important properties in this table. For example, property 8, that Laplace transform of convolution is a product. Laplace transform of a product like this with step function is function like this. Laplace transform of step function, window function, delta function, Laplace transform of derivative, of the first derivative, for example, here, of the nth derivative here, for example, and many other properties. So, and also using this table, you can of course find inverse Laplace transforms. You just find what you need in the second or fourth table. For example, inverse Laplace transform of this function is sine bt, and so on. But even this table will be given to you, you have to learn how to use it. You have to know what you have in this table, so to find things quickly. Okay, therefore you have to solve a lot of problems and you have to do a lot of practice on this Laplace transform. So don't think like this, okay, this table, everything will be given to me, so I don't have to learn anything. No, this is not true. You have to learn a lot. So I think this is it, what I wanted to say about Laplace transform. And the rest of the material will be devoted to solving systems, linear systems of differential equations.